Hello and welcome to our next lesson of financial literacy. Today we are looking at solving financial problems. So by now you've seen simple interest, compound interest, and specifically how compound interest works with regards to compounding periods and different rates per year. And so now we're putting all of that together and we're going to be solving for different parts of the formula or like different variables. And we're going to see a mix of everything. And this should also help you get more familiarized with solving problems with the formula from last lesson as well. So, just some key vocabulary that might help you throughout this lesson. So, either for the practice problems, and this is a bit of a review, but remember exponential growth, which is also for compound interest, is pretty much a process where whatever principal amount or quantity that you start with is growing by a constant percentage rate each period. And that period, as we saw, could be yearly, could be monthly, or different periods as well. Now we have doubling time, which is the in terms of financial literacy, for us, it will be the period that it takes for an investment to double. Previously, we saw doubling time with, for example, population of bacteria, and doubling time could be how much it takes for the population to double. But now, when we're talking with money, it's how much for the amount that we've invested to double. So our first question, we're going to be actually solving for the number of periods. So, how many years will it take for $1,000 to double at 5% per annual interest compounded annually? So, we've seen questions like this for exponential functions where we were solving for the exponent part. So, this is similar. Now we're also solving for the exponent here. And since the account is compounded annually, we do know that the interest per period is going to be the same as the rate, which is 5% or 0.05. So we want to find a t or n exponent that we're going to have 2,000, which is double 1,000 because we want it to double, equal to 1,000 times 1.05, again, our rate here, to the power of t. And if I divide by 1,000 on both sides, or again, just thinking, I want this to double, right? So even if I invest $1 and for that to double to $2, it's going to be the same amount. So 2 is going to be equal to 1.05 to the power of t. So we want to know what this t is or how many years it would take for it to double. And I do suggest you take a moment and use trial and error. And again, just try any small value you can think of. Maybe start with 5 and see what value you get. And based on that, keep increasing the value or decreasing it to get a more exact value. And so you should have got a general answer by now. And I am going to show you the actual method for how you would solve it. Now, the method that we're going to see is not a requirement for this course, so I'm just showing it to you in case you are interested or you were curious about it, so you do know there is actually a strategy for this, but again, you're not expected to be able to use this. So, as we know, in mathematics, there's always an inverse operation. So when we have multiplication, if we have 5 times 5 is 25, then we also know that if I apply the inverse function, which is division, so 25 divided by 5 should give me that 5 as well. Or if I tell you the product of 6 and a number is 48, what is that number? Then really you're doing 48 divided by 6 to get that value, which would be 8. And there is actually a inverse operation for exponentials, and it is logarithms. So the definition of logarithms would be the inverse operation of exponentials, and it pretty much would tell us what that value of t is. And so I will include a link for you if you are interested to learn more about logarithms, but you can always search that on your own as well. There's lots of videos and resources online if you would like to learn more. We will see a little bit of how it is used in this lesson, but again, you're not expected to know this for the course. So here I'm just telling you the answer, but if we were to take the logarithm of both sides, then we would get that t is equal to 14.21. So that means after approximately 14 years, then the $1,000 has doubled to $2,000. Or again, even if we invest $1, it's going to be doubled to $2 after approximately 14 years. And of course, when we don't have logarithms, we would do trial and error. So compare your value that you got from trial and error to 14.21 and see how close to you perhaps were. Now, I'm also going to show you the graph because really, this is just an exponential function, 1.05 to the power of t with a base of 1.05, and 2 can be interpreted as just a line. So I could split this up into two functions. I could say, and just to match the colors I have here, I could say f of t is equal to 1.05 to the power of t, and then I also have y is equal to 2. So y is equal to 2 is going to be my horizontal line, which intersects the y-axis at 2. And this one here, the red function, is just an exponential function. So if we were to graph each of these separately, which is what I've done here, and I match the colors, so y is equal to 1.05 to the power of t is the red function shown here. And y is equal to 2, as mentioned, is that horizontal line with the value of 2. And the point of intersection of these two, which is also the same if we were to say, when are these two, for what t value are these two functions going to intersect? Then we would get over here 14.2067. So if you round that to two decimal places, that's also 14.21. And that's exactly what logarithms are doing for us as well. They're telling us at one point is this intersecting for this exponent value here to produce an output of 2. And you can now try for yourself. 1.005 to the power of 14.21 will give you 2. Let's see what logarithms are. So a logarithm tells us the exponent to which a base must be raised to get a given number. So when I said above, we took the logarithm of both sides, we're actually doing this operation over here. So our base would have been 1.05. So maybe let me write it for you in blue. 1.05. And we want to know for what exponent will 1.05 be equal to, and here is our output, or x would be 2 here, which is the output that we wanted. And then the y that we're going to get here will be that 14.21, which was the exponent that we wanted. Or to give you a more simple example, of course we know that 2 to the power of 3, or 2 cubed, is equal to 8, which means that the logarithm of 8 with base 2 will give you 3, which means what power do I need to raise 2 by to get 8? And of course that power is 3. Couple more examples here for you. So if you have 2 to the power of x is equal to 32, then we pretty much want to know what x has to be for this to be true. And you might already recognize 32 as a power of 2, but if you didn't, you would just do the logarithm base 2 of 32 and you get 5. And of course, that means x would be 5, which means 2 to the power of 5 will give you 32. And you can check that's exactly what you would get as well. If we also have 3 to the power of 2x is equal to 81, we're still trying to figure out what that exponent is. But now we have to keep in mind when we solve for x, this is 2x. The exponent is really 2x, and then we're trying to solve for x. So really, we first want to know what this exponent has to be. So then, the log of base 3 of 81 is going to give you 4, which means that 3 to the power of 4 is going to be equal to 81. But remember, the power was 2x, so then x would just be equal to 2. And so if you're solving problems with exponents and you have different expressions there, that's the process you would solve. You could even have 3 to the power of x minus 1 is equal to 81. You would then also see that x minus 1 would be equal to 4, so then x is equal to 5. Oh, and so how this is going to help us with financial literacy, again, as we saw with problems like these, or just with exponential problems as well, when we're solving for the exponent, we can always use logarithms. So if you want to learn more about it, then you can, of course, learn more and try to find exact values. But for the sake of this course, if you do trial and error to estimate the number of years to the closest year, that would be fine. So even if you had got 14 years here, that would be a good answer. You're just saying after 14, approximately 14 years. Now our next problem. And we're still going off with that doubling of our investment. So here we have $10,000 and we want to know how many years it will take for $10,000 to double if it's compounded annually at 3%, 6%, or 12%. So in this case, you're not doing, well, you're kind of doing trial and error, but using the table. So take a moment and try to complete all of these on your own. And maybe I'll support with just the first row. So because this is annual, compounded annually, then the rate just stays. So this one would be $10,000 times one plus 0.03, and after 6 years would be to the power of 6. And I will find a value here. 3 to the power of 6. And this will be 11,940. And maybe let's round to nearest dollar. And for the next one, the $10,000, now 1 plus 0.06 because it's 6%. So, and if your calculator has a backspace button, by all means use that instead of rewriting it each time. Or you can always use Desmos as a calculator as well, because you can always just erase and write and it gives you the output right there. So this one will be 14,185, and finally with 12%. We would have, so this would be 10,000 times 1.12 to the power of 6, and we would get equals 19,738. Okay, and so already I can see this one is pretty much doubled at this point, maybe just a little bit more. So try to fill out the rest of the table and see what values that you get, or how many years we require for the 3% rate and the 6% rate to double as well. But these are all the values you should have got if you were just rounding to the nearest dollar. So now we're looking at the number of years that have passed for all of these to double. So first, let's look at the 3% rate. So, of course, looking at the final of the or the total of the table, after 48 years, $10,000 will become $41,000 for us. But approximately after 24 years, we see that the amount has doubled. Now, for the 6% rate, if we save for 48 years, we're going to have $163,000, or close to 164,000. But again, the doubling time will be after 12 years. And for the 12%, we will go with this value. So approximately after 6 years. And of course, if we save up for the full 48 years, we will have more than $2 million. So such a great rate for investments, of course. And now you're asked, what do you notice about the doubling time at each of the different rates, and what pattern do you notice? So with the 12%, it was 6 years. And when the rate is split into half, so 6%, then we see that that year is also now doubled as well. So instead of 6 years, it's 12 years. Now, with the 3% rate going from 6%, this is also another half. So instead of 12 years, now that year is also doubled to 24. Or if I were going from the 12% rate to go down from 12% to 3%, that's a division by 4. So then the number of years goes from 6 years to times 4, 24 years. So of course there is a pattern there, and it does affect the doubling time of the different rates. And it's just interesting to see also when you are comparing rates, a lot of financial institutions do offer comparisons for you to see what your investment will look like at each different rate that you invest. Now, with financial literacy, there's the rule of 72. So this is, of course, an estimate. It is not a solid formula that works at all times, but as a general rule, it's an interesting rule that works and can be used sometimes to calculate the doubling period. So the rule of 72 is an estimate of how many years it takes for an amount to double at a fixed annual interest rate, which means that your rate is not changing. So even if you're compounding like annually for 5 years, then the rate is the same over those 5 years. Whereas there are some other investment options where the rate actually fluctuates. So that's not a fixed rate. So we're considering fixed rates where over a certain amount of years that you're investing, that rate is not going to change. So what you do is you divide 72 by the interest rate, and that will give you the number of years. So for example, when we just had 72 divided by 12, then we got 6, which was 6 years, as we just saw here. Or if we had 72 divided by 6, we would get also 12, which is now 12 years. Or if we do 72 divided by 3%, or the 3 from the 3%, we would get 24, which is does match with that 24 years that we just saw. And so pretty much you just have to know the rate, and then you divide 72 by that rate, and it gives you the approximate value. Now, one thing I'll point out, this does talk about annual rate here, but even if you were considering compounding at different compounding periods, this could still work. So for example, let's say you are compounding monthly and you have a 12% rate. Then 72 would be divided by the rate per the compounding period. So let me just write it for you here. So it's 12% annually and then compounded monthly. So what we would do is 72 divided by, and the interest here would actually be 0.12 divided by 12, which is 0.1. And so this is 1%. Sorry, 0.01, which is 1%. And so really you would be dividing by 1 here, which is that 1%, and you would get 72. But the 72 does not mean 72 years. It means 72 months because that's what we were compounding. So if I do 10,000 times 1 plus 0.12 divided by 12, or this is just 0.01. And now I compound the 72 times, so to the power of 72. Then the answer you get is 20,471, which is precisely double. And so that means it does take approximately 72 months or 6 years, which again also matches with that 12% rate that we saw, because this is an estimate. So perhaps maybe the month before you're also really close to 20,000, but for sure after 72 months, we can for sure say that we have the double the amount. So let's just practice now here. So we have $15,000 and we're wondering how long or how many years would it take to double at each of these rates. And for now, we're considering just annual. So in the 8%, this would be 72 divided by 8. Oh, so just 9 years. This would take 9 years. Here we would do 72 divided by 15, or It is equal to 9 years, but again, remember this is just an approximation. So in your final answer, if you're writing it, you would say approximately 9 years. This one would be 4.8 years. And at 4, it would be 18 years. Okay. And now I do suggest you try this on your own and check your answers. So I'll just show you maybe one of them. So if we have 15,000 and now it's 0.08, and now we're use the answer here. So 9. So we would get 15,000 times 1.08 to the power of 9. This gives us 29,985. And for an estimate, that was really close. That's double 15,000. We're almost at 30K. So that was how we check our answer as well. So you can now try for 15% and 4%. In this next example here now, we're asked to find the annual interest rate if $1,500 grows to $1,800 in 10 years. And this is compounded annually. So again, think of the values that were given. This is our future, this is our present value. This is our future value. And this is the number of years and or t. Now, using our formula, we want 1,800 to equal to 1,500 for an interest that the rate that we're trying to find, so 1 plus I to the power of 10. So now we're just solving for I. So this is just a little bit of algebra to solve for I. So we divide by 1,500 on both sides. So we get 1.2 is equal to 1 plus I to the power of 10. And now this is our exponentials. So we take the root and we take the 10th root because it's an exponent of 10. So remember that's on your calculator, you would have a radical with 10 there, or you would do 1.2 to the power of 1 over 10. And you should get 1.0184. And this is equal to 1 plus I, which then means that I is equal to 1.0184 minus 1 or 0.0184 or 1.84%. So then the annual interest rate is approximately 1.84%. And of course, please do check your answers at the end, just to double check. And make sure that you did solve it. So you would just input this value here for 1,500 and then solve and see that you actually do get 1,800. Now, in the next problem, if you need $5,000 in 12 years and the account pays 3% quarterly, how much should you invest now? Now, here we're solving for the present value, so P or PV. And because the account pays quarterly and it's 12 years, that's 48 compounding periods for us. And our interest would be R divided by N. And so because it's quarterly, that means 4 times per year. So 0.03, which is the 3%, is going to be divided by 4, and it gives us 0.75%. Now using our formula, now here, the present value is going to be equal to $5,000, which is what we want in the future, and divided by 1 plus 0.0075, that's 0.75%, and compounded 48 times. And this is, the value here is 3,493.07. And if we round up, we need to invest $3,494 today as our present value to earn $5,000 in 12 years in an account that pays 3% quarterly. I mean, that part is already in the question itself, but just a repetition for you to remember as well. And of course, if the rate changes, if the compounding period changes, or if the number of year changes, your p-value is going to change as well. And this is our last example. So Nicholas had a credit card balance of $550 that was 31 days overdue. The annual interest rate on the card is 23.9%. And if you have gotten a credit card or if you've looked at credit cards, you will see the rates are pretty much really close to this. And so, of course, that's why it's always suggested when you're getting credit cards. So exercise caution, make sure you're paying on time because if that interest is applied, you're paying a lot of money. So here we're asked how much interest did Nicholas have to pay. So here I've added a note for you that credit card rates calculated for the month are simple interest. What I mean by that is that when they calculate it for that month, they look at each month on its own. So the reason for that, of course, is because if they look at it this month and then next month you make some payments, then of course that amount has changed. So it is fluctuating. So it is different from compound interest in the sense that we cannot use that formula because your present value is changing. So that's why you have to look at it month per month. And then if you're looking at it in that month on its own, then it is kind of like a simple interest for that month. But of course, if you do not pay, then the interest does accumulate the next month. So next month you have to pay whatever you haven't paid and the balance on top. So for example, with the $550, that's 31 days overdue. So there's going to be an interest on this already. But if the next month that amount is not paid and even more is accumulated, then that's a whole new present value that we're looking at. So you would then pay on this, the interest, and any new amounts that you've accumulated on your credit card as well. So in this case, the rate being 23.9%, then that's 0.239. And this is actually for credit cards, this is compounded daily. And the reason for that is because month per month, the number of days changes, right? So credit card company thinks if you have more days, then it's more days that like more opportunities to be paying it. So they do calculate it by day. So in this case, then we have our compounding period is going to be 365 days. So because he was late by 31 days, we have to consider what portion of that he was late for. So 31 days over 365 days. And again, I'm keeping this as a fraction to use in my formula. So the interest is going to be the $550 times the interest times the amount of time, which in this case is 31 days of the 365. Or you could have also thought of this as the interest rate per that period, which is the day, is 0.239 divided by 365. And then you're thinking, oh, how many days was this accumulated? 31 days. So times 31. And really, this is just this denominator move from here to here. The same answer is produced. And the interest is $11.16. So he has accumulated $11.16. And how much interest does he have to pay is this amount. So he does have to pay a total of $561.16 because he still has to pay the amount that he was charged. But of that, $11.16 are interest. Now, if the following month, which is another 30 days, he still has not paid his balance and he spent another $670, how much will he have to pay? So now he already has this balance from the interest that was accumulated, and he spent another $670, which means now he owes that amount plus the 670, which is $1,231.16. Now, because this is a new month, interest is calculated again on this new value. So again, we do have to divide our interest by the number of days. And then in this case, we were told it's 30 days. So we multiply by 30. And the total here is $1,255.34. Now, in this question, we weren't asked how much interest, it's just how much will he have to pay. So you do need to account for the total and the interest. But you might have been asked how much interest he has to pay, so all you would have to do is subtract the starting balance from the amount that you just calculated, or just from here, we would get $24.18, and that's how much interest he pays. And how much total interest does he have to pay after 2 months? So now For this question, we are considering the next month if he doesn't spend any more, for example, how much would he have to pay? And in this case, it's pretty simple. You're just calculating the interest on this amount, and you don't have any new spendings. So you would calculate that interest, and then that's the interest for the second month, and then we would have to add this interest from the first month to calculate over those 2 months how much he paid. And that was our last example for this lesson. So you have some practice problems here. As always, please check Google Classroom for any additional tasks. Don't hesitate to reach out if you have any questions, and I will see you all in our next class.